Okay. Hello, everyone. My name is Kartika, and welcome back to the rest of the session 2. Just a quick recap, we were talking about constrained optimization, and we have seen a very mathematical, synthetical way of solving a constrained optimization problem. Later, we have seen the nuances behind switching it from a simplistic problem statement to a little bit more complicated problem statement and solving it using one algorithm from nature-inspired computing. So I'll start from there. So we have seen what goes inside a genetic algorithm, right? How does it work? We have even seen a demo. Now let's port it to a realistic problem statement. So we started with flight scheduling as the problem, right? So let's talk about a quick recap about the flight scheduling problem. What are we trying to do? We have several flights to assign resources to, and the resources being aircraft, crew member, pilots, etc. to the aircraft. So now we have to formulate this problem to fit into the GA paradigm, right? So what are we trying to do here? We need to maximize or minimize a fitness function. And in this problem statement, we are trying to maximize the fitness. And what is the fitness here? As CEO of Sahaj Air, we need to maximize our profit. Now, what's profit? Simple, right? Total revenue generated minus total cost incurred. Very simple. So this is what we have to maximize. And what's the total cost? In the current framework of our problem statement, we have operating cost for the aircraft. We have salary to pay to the pilots as well as salary to pay to the crew members. So there are three components. Put them together. That's my total cost incurred. And revenue generated is revenue generated. Now, what are the constraints that we have to stick to while I maximize this problem? I can just think about maximizing the problem, cut all the salary from the crew members, pilot, forget about the convenience of people who are traveling and just go and maximize the problem, right? If I do that, Sahaj Air will get bankrupt and get closed in like no time. So we need to adhere to certain constraints. What are the constraints? I don't have all the budget in the world. I don't even have capital in the world to assign, like, let's say 100 flights and covering 10,000 cities, right? So I have a budget cap. So the operating cost of the aircrafts plus the total cost incurred, I have to limit it within a budget. It could be a daily budget, it could be a weekly budget, monthly budget, whatever it is. Now, the second constraint that is, I need to comply to certain legal limits for carbon emission. Many countries impose that over airlines now, and we need to minimize the carbon emissions from the flight getting operated. Then I need to also assign crew members so that they are not overworked. So I need to restrict the crew members' operating hours to less than 8 hours or whatever. And then I need 2 unique pilots and 3 unique crew members on every flight. So these are all the constraints that I am going to adhere to. Now, what are we going to do here? What should we do here is we need to mathematically frame the problem statement. So I'll call out one very specific difference between framing this problem as a linear programming solution versus a GA solution, not just the nonlinearity. What I have to do here is, in LP, I can just throw these constraints, put all crew members working hours under 8 hours. I need to get the total operating cost under budget. Just give it as less than constraints. But for a GA to work, I need to be smart enough to formulate my problem mathematically in a fashion that it fits to a non-convex optimization problem. I am giving enough flexibility for the algorithm to move around rather than following a straight line, move around and find solution. Where will this come from? As a developer of this problem statement, I need to be smart enough to formulate this problem mathematically in a way that RGA is going to accurately work and converge faster. So I'm going to talk about that now. So the revenue minus cost part is just that. I cannot do anything with that. So that part is still there. I'm going to maximize it. Now I need to add penalties for constraints, right? So I have Little bit of a harder constraint. This is all, make believe. Don't relate it to a real flight scheduling problem. So let's say carbon emission is a harder constraint or a stricter constraint because let's say it's a government norm. So on an average, I have to stay within the carbon emission limit plus or minus some values. So this is a harder constraint, and I am giving like a huge penalty, like 1,000, let's say 1,000 or 5,000, if I overrun the carbon emission limit. So what is overrun? Actual carbon emissions produced by the flight minus the limit. That's the overrun. And if my overrun exists, even if it is like 0.1 is the overrun, I apply a penalty 1,000 blindly or 10,000. Now, what are the other stricter constraints here? I need 2 pilots for each flight. That's non-negotiable, right? And I need 3 crew members for each flight. That's also non-negotiable. So I apply like a huge penalty for that. If same algorithm doesn't know, it only knows the IDs of the pilots, right? So it can pick the same pilot twice and call it as 2 pilots. So we should penalize that kind of decision. Huge penalty. Same aircraft to 2 flights going on at the same time. What will happen? So huge penalty, 10,000. And all these are actually scaled with respect to the budget. It cannot be unrealistic. So I cannot say the penalty is infinite. The algorithm is not going to converge. So these are scaled versions of my total budget. So if I have a 500,000 budget, then I kind of scale it with respect to, okay, for 500,000 budget, maybe 10,000 is a good penalty for duplicate aircraft assignment. For duplicate crew, it's 1K is okay. Carbon emission, maybe 1K is okay or 10K is okay. So this is how I assign huge penalty, heavy penalty for strict constraints. Now what happens to the softer constraint? The cost equation we have already seen. We have a daily budget, but many a times what will happen is I have to schedule 50 flights for the next 3 days, and it may slightly overrun the budget. So I cannot completely say that I should operate within the budget. If I say that, some or other flights may go out of scheduling. So here I'll say that, okay, this penalty I'm going to assign little softly. Okay, so if the overrun is small, I'll give a small penalty. If the overrun starts increasing, I'll give a heavier penalty. So that is a non-linear penalty function as shown in this graph. So if the overrun is towards the 0 side, the penalty is slower. As and when the overrun increases, the penalty actually shoots up really fast, and then it kind of stabilizes after a point. Okay, this is a non-linear penalty function, and a classic function alpha plus 1 x divided by alpha x plus 1. This is a classic non-linear penalty function. I'm going to apply a similar penalty over the crew hours also. Let's say we have a 9 hours flight. I cannot say that my pilot should exit mid-flight after 8 hours and another set of pilot jump in, right? I cannot do that. So basically, I have to say that, oh, this particular crew has to work 1 hour extra. Maybe I'll pay for overtime, or maybe I'll adjust that same crew's allotment in the next flight to go on a 3-hour flight. So that on an average there, 8 hours is kind of maintained. So it's a softer penalty, and I cannot enforce this because flight durations vary. So this is the mathematical formulation behind it, and why the math is important. As I already said, whenever we have nonlinear functions, we are giving a flexibility for the algorithm to go a little away from that one straight linear constraint, or in this case, gradient descent, right? Like we are actually moving downstairs in the gradient way, and instead of going down that strict non-linear way of gradient descent, look a little bit in a windowish manner here and there. So it is we are giving the algorithm explorative capability, and going like downstairs in that gradient descent fashion is exploitative capability. So this is a balance between exploration and exploitation. And that's why that mathematical formulation is important for GA, and the onus is on us as opposed to LP, throw it everything. When the problem is in the linear space, it will solve it by itself, whereas GA or any swarm-based technique requires a little bit of design on the mathematical equations part so that the fitness is carefully crafted. And now, what is our fitness? To maximize, it is revenue minus total cost, which is the profit, plus minus all the penalties for budget overrun, crew hours overrun, emission overrun, and penalty for non-unique crew and aircraft assignments, out of which 3 are stricter constraints, huge penalty, 2 are softer constraints, little lesser penalty. And this is the fitness function of the genome that the GA will maximize. And we already saw how it works. So the genome here is nothing but for a flight I, pick the aircraft AI, 2 pilots P1I and P2I, and 3 crew members C1, C2, C3. And this will extend for all the flight. If you have 50 flights to schedule, 50 into 7 is your genome length. And this is what the GA will find while doing the, doing the tricks that you've already seen, crossover, mutation, tournament selection, etc., etc. And it will hit convergence. So this is the fitness evolution over the number of generations. As you can see, the fitness is getting maximized. After a point of time, it's getting Ripley, pretty much stabilized, and we call it a solution. Now, the fitness function that we were maximizing, it had multiple terms, right? The profit was there, the carbon emissions were there, cost budget constraint was were there, etc. So this is the evolution of those constraints also. So when we maximize the fitness, it is not just that we are maximizing the profit, but we are also making sure that the carbon emission stays within the limit. As you can see, it is 1993.48, which is less than 2000, and 2000 is the set cap limit for this problem, and the budget is 500,000, and our optimizer is able to find an optimum solution which only costs 312k rupees, dollars, whatever it is. Okay, so the constraints are met, and we got a best fitness function. And this is the assignment. So now, if you remember, we assigned penalty for duplicate aircrafts, duplicate crew, right? So if you see over here, oh, you can't see. Sorry, I thought my cursor is moving. So if you see that little bit line kind of thing that's happening over there, right? So what does it mean is the same aircraft A10 is getting assigned to a lot of flights. So it's not sticking to the penalty. Oh, you can't? Sorry. I zoom it. Never mind, I'll say what it is. So basically, what does it do is, even though I applied a huge penalty, don't pick the same aircraft for different flights. It is picking the same aircraft for different flights. And from the figure, I'll just read it out. If there is an aircraft A10, it is actually getting picked for flight 1, flight 3, flight 7, flight 13, flight 19, etc. This is an undesirable behavior. But in an airline scheduling, this is bound to happen. If the same aircraft is there and it's a high performing aircraft with respect to fuel efficiency, carbon emission, etc. And if you have 2 flights to schedule at 2 different times, you can still pick the same aircraft for the 2 different flights, right? As long as the flights are not, going to fly at the same time. You still can do that. That's why it is not we did not code it inside the problem. Instead, we applied a penalty for the problem. But we still have to diversify. We have to make sure that one aircraft is not super overutilized and some aircrafts are underutilized. We want to avoid that scenario. So even though GA is giving you an optimum solution, it is faltering in some spaces because it is giving you an optimal solution to the best possible sense. So all these heuristic and meta-heuristic algorithms, what does it do is, it will give you a solution which is to the best of my knowledge. That's the term. Okay? To the best of its knowledge, this is the optimum solution. May not be optimum in real world at all. The same goes with, pilot assignments. Pilot assignments, we have actually hard-coded for same flight, don't put the same pilot. So that constraint is getting adhered to because we coded it in. But the same pilot may get picked for 2 different flights. Again, the same problem. If the flights are at different times, it's okay. But if they are on the same time, this is again undesirable behavior. And this is like the crew overworking heat map. So the reds are like the crew are like really overworked around 20 hours. I mean, it's not daily, so should be okay. And some crew are underworked. This is also desired behavior in the sense that we don't want 2 senior pilots on the, or maybe senior pilots the pool is less. So we may have to make them little bit overwork, whereas our intern sort of pilots, maybe that pool is larger and some of them will get underutilized, which is okay, which is a desired behavior. But we have to hit a balance between all these. So GA or any meta heuristic population-based algorithms will give you an optimum solution to the best of its knowledge, and we may have to tweak it before implementing it, or maybe not. It may be an actually optimum solution. So just to conclude on the GA bit, what does it do? It gives optimum possible allocation of flight by maximizing a fitness. And fitness is nothing but our objective for this problem, which is profit maximization. And constraints are governed by penalty functions. And if there are like strict hard constraints, we will actually hard code it into the code. Need a mathematical problem formulation, very important. We need to design a mathematical problem formulation for GA to work accurately and converge faster. Otherwise, it will never converge. For more complex problems, then this action that it needs to take, right? There are like 5,000 flights to schedule and you have 50,000 aircrafts. The choices becomes NP hard kind of a problem, right? Then the problems itself will become complex and GA convergence will be super slow, okay? And when it start to become dynamic and adaptive, classic example is flight scheduling, weather problems, runway did not get clear, flight delays, flight cancellations, crew fatigue, or these are adaptive constraints or dynamic constraints. GA doesn't care about this. It will schedule all flight at once depending on the data at that time, and it won't evolve its behavior with respect to change in data. And sequential scheduling, again, it doesn't do that. It schedules all of the flights at once. So the classic problem, right? If I had a way to schedule flight 1 first, then I knew that the crew got allocated to that flight and aircraft that allocated to that flight will get cleared after that flight duration of 10 hours. Then I can actually assign the same crew to flight 5, which is about to take off after the 10 hours. This is not a luxury that we have in GA. So how do we go about it? We'll go into real, AI space, if you want to call it. So RL comes in. Why do we need RL? I think I already answered the question. Complexity is on the rise. You have a lot of flights, and Sahaj Air is now a very big airline company, and we have a lot of choices. Then the problem gets hard. So the number of crews, the number of aircrafts getting hard. Plus, we need to look into the adaptive constraints also. Let's say weather changed. What does if there are turbulence? Then what happens is your craft will burn more fuel navigating the turbulence, which essentially accounts to, which essentially affects its operating cost, more fuel burned than actual estimated fuel. So when it lands, it has less fuel than you think it would be. Then what happens? The carbon emissions, of course, it will also increase because of weather factors. And crew availability can randomly change. Maybe like somebody called in sick on the last minute. Then you need to adjust that in your scheduling. So all these are complexities that will happen in your flight scheduling problem. And RL is a very viable answer to such a problem. Now let's see what is RL, right? So if we look at the evolution of the techniques that we have seen today, LP, very mathematical, very synthetic, very easy also, but you need to know that lines, feasibility region, etc., in order to put it into the solver. So that's a very synthetic way. Second class of algorithms, we looked into the nature, right? We looked out and we thought, oh, this is how evolution works. This is how organisms work. And there is a whole bunch of class of algorithms in nature-inspired computing: fish schooling, bird flocking, ant colony, particle swarm, genetic algorithm, etc., etc. We have seen genetic algorithm in detail. This is nature-inspired computing. You are basically looking outside. Now, when it comes to AI, I know this is all AI, to be very honest. But we talk about neural networks specifically. That was our attempt to look inward. How does human beings work? I mean, other organisms also work in similarish way, but let's stick with human beings for today. So how do we work? So the first neuron that we have designed is our attempt to replicate our brain cell neuron. Then we scaled it up by magnitudes. It became deep neural network, deep learning, right? That's how our brain operates. And RL is a classic example of simulating or emulating classic human behavior to solve a problem. Let's take an example. I am getting a training done from L&T Training Institute, and I am going from Pune. I took the train, and then I got down at Lonavala railway station. Okay. Uh, so how many of you know about supervised learning, unsupervised learning, etc.? You know the idea. Good, great. So I got down from the train at Lonavala railway station. What would be a supervised training example? Ideal scenario, let's say L&T ka some guide or like a person who's responsible for my training comes to the railway station and pick me from there, go directly to the training institute. That would be an example of supervised training because it's a labeled data. That person know where my destination is and I am just going with that person. So that's supervised training. Now, what's unsupervised training? I can, before going to Lonavala railway station, I Google mapped and then I asked around my friends and collected all the data that I can get. And even in this case, Google suggests me 2 routes, right? There are 2 routes on this. Maybe there is a third route that Google does. Okay, that's unrealistic. But let's say there is like a very shortcut that my friend suggested me, etc., etc. I put all these data in. I don't know which one is better, but I kind of crunch this through the data and make a sense in my head, thinking that, oh, this may be a good route. That's unsupervised learning. I figure it out from the data. Now, what is reinforcement learning? I don't have any data. I got down at Lonavala railway station. Maybe I have like a compass. Okay, bear with me. Bad example, maybe. But I got down at Lonavala railway station and I started walking, like aimlessly. Then I know that I have to go north a little bit because I have a compass. That's a feature that I have. I started walking. On the way, I saw that Hotel Ramakrishna is there. Then I went to a particular turning. I took the wrong turn. And I saw there is a German bakery over there, Lonavala. And then I hit a roadblock, like there is a dead end. I came back and then I walked all the way. Finally, I reached this institute. Now, what did I do? I explore. Okay, I take one step at a time and I see, look at my compass, I'm heading in the right direction. Maybe I have a random distance calculator saying that I'm getting closer to my destination or not. Let's say that I have it. Then I looked at all these and I finally reached. It's a not efficient way of reaching that institute as compared to my supervised learning where a person come and pick me. It's not efficient. I lost a bunch of time. But think about it. On the way to solve that problem, I also solved another bunch of problems. Now imagine my training is for a month. After 1 week, I got really bored about their mess food. I know there is a German bakery on the way. So on a Sunday, I can just go and have food from German bakery. Then if the Hotel Ramakrishna is like authentic Marathi food, I'll just go there and eat it because I got bored of my food in mess. Similarly, other things. So basically, even though I lost my time, even though it was not a very great way of getting to the institute in the first place, I solved a bunch of other problems that may come in my way in the future because I kind of now built a whole understanding of that landscape of the problem. This is what RL does. And tomorrow I get a new problem, like I am craving for, I don't know, buns or something, then I know where to go. So I solved some bit of problems ahead of time. This is RL. Now, how does this pan out to an actual framework that we can implement and solve? There are 3 components. There is an environment. Environment is nothing, just environment. In the maps example, that map with all the features, the compass I have, the distance calculator I have, this is all in my environment. And the environment produces a state. What's a state? It could be the distance left to the training institute, the compass saying that north is this way, etc. And depending on and there is an agent which takes an action. In this case, it's me because I'm the one who is walking. Oops, sorry. So what do I do? I take a look at the state, my compass, my distance calculator, maybe some previous steps that I have followed. Like I took 3 steps to the right and then 1 step to the left. Looks like I have to change. So I take an action, which is, okay, let's go to the left again. Now I take a look at the environment back. Where have I reached? So the environment, take a look at the recent action that I took, and it evaluates that action and it produces its next state. So I get closer to the L&D institute, or maybe I get farther away from the institute. That's a new state. Together with that state, it also evaluates that action with respect to the state and provides a reward. So if I'm heading in the right direction, it will say +1. If I'm heading in the wrong direction, it will say -1. And this is the reward. Now the agent, me, I have new state to look at and the reward that I got. So the agent takes the reward and the current new state, take a new action. And this follows. This is exploration, and then I will finally reach somewhere. Now, how do we actually implement it? This is all well and good in storyline. How do we actually implement it? We have to rely on something called a Markov decision process or a state space model. Don't get thrown away by the jargons. So basically what I have to look at is a space of all my states. So if I have a compass, what can it show? It can show the north and maybe like little deflection towards this side and that side. So that's my state with respect to the compass. What's my state with respect to the distance computing device? Just one value, distance, actual distance, or maybe an indication that distance is getting reduced or distance is getting increased. That's a state. Maybe all the steps that I've traced in the history, that's also my state. Now, using this state, I take an action, A0, and I get a reward, R0. I go to the next state, S1, take another action, get the reward for that action, go to the next state, and then continue this flow. So all my state space is the combination of all the potential states that can exist in this universe of the problem. And all my action spaces, the steps that I can take. Maybe I can take 1 step right, 1 step left, 1 step forward, 1 step backward. This is all the actions that I can potentially take. So that is state space and action space. Now, what is my intention? Is to maximize the reward, right? I have to keep taking action so that I get more and more reward, collect more and more game points in a game theory. Now, how do I implement this reward, right? So cumulative reward, that's what I have to implement. I should not take a look at the local reward. So I should not just see that I'm getting a reward at this time. Instead, I should actually think into the future and look at the cumulative reward I'll get when I reach the training institute. Another analogy to this is, let's say, a chess game, and you have seen this, right? Sometimes we may have to sacrifice a pawn to capture the queen. Okay, so the bigger reward is queen, but at this instant of time or at this moment, I lost and I got a negative reward because I lost the pawn. So that's the idea. So we should not look at the local reward. We should look at the global reward or the cumulative reward. Look into the future. So cumulative reward in this case is this R1 plus R2, R0 plus R1 plus R2, etc. for all the chain that you are following. Now there is one more term called discount. What does that mean? So when we take actions and look farther into the future, things get hazy, right? A lot of uncertainty can happen when we look very much farther into the future. So you place less weight for the reward that you expect 100 moves from now, and you place a lot of trust and lot of weights at the immediate rewards, but not in an absolute sense. You will lose a pawn, you will get a negative reward, not just immediately. You take a linear combination, non-linear combination of all the rewards. So if gamma is a constant less than 1, you will actually take the immediate reward plus gamma times the next step reward plus gamma square times the next step reward, etc. And gamma decreases as you go in the future. And sum it up together, you get something called DCFR, or discounted cumulative future reward. Okay, and this is, yes. Yeah, so, sorry. Mm. Yes, so basically the first question is, what if the space is infinite, right? That's what your question. Both spaces, the spaces that we consider are infinite. Those kind of spaces are called continuous spaces. Okay, continuous spaces has infinite possibilities, like anything between 0 and 1. Anything between 0 and 1 has infinite possibilities. Yes, so in a continuous space, what generally we will do is we won't consider it as a discrete action to take. Instead, it will be a continuous function that we will navigate. So we will write down the problem statement in such a way that it is a, let's say, a sine wave or a cos wave. So even though the possibilities are infinite, cos t has a value at t, right? So that will emulate your action. And there are algorithms that navigates continuous space. Now, the example that I mentioned, it was like I mean, simplistic enough to get an example. For example, the meteorological data, and you need to tune or calibrate your devices to catch a future event based on the past meteorological data. It's a classic example of continuous spaces. And then you actually capture the continuous space as a function. Like in GA also we saw, right? It's a non-convex surface that we are navigating. Similar thing will happen here, and we will have functional representations. Whereas in discrete spaces, you will have discrete set of action. Even that can be infinite, right? 0 to infinity, but all integers, z. That's an right. It's a modeling strategy. Basically, this is all banking on hidden Markov models. That's the space. That's the idea that we navigated to make RL possible. And then there are multiple algorithms that work on that formulation. So if you know hidden Markov model, there is a probabilistic set of training that happens over there. Here we banked on the exact same state space model, and we are trying to do it in a non unsupervised kind of way. So it's a mixture of both. You have good idea of the problem statement so that you can write the Markovian equations from there. Now on top of that, you do something unsupervised. So it's a combination of both. That's why it's called reinforcement. That's why it's a third class of algorithms called reinforcement learning. Got it? So that's the second question, right? So the second question is, when I write this R0, R1, etc., I actually are only looking at the future. So till now I have done. So I know there is, I know the rewards that I have collected already. Now I try to find the possibilities from there, and I say that if I go this path, I'll get this much reward. But if I go this path, I'll get a different reward. Now, depending on that estimated reward, I would say this is a not a good path. I would rather take this path. So it's only the future reward. So the equation actually is summation over k, gamma k. Sorry? Yes, it's an expectation. We'll come to that. I just put the function as it is. This is what we are maximizing on. But since this is in future, it is expectation anyway. Okay, so this is the function that we are maximizing. We'll come to the formulation in like 2 slides or something. Cool. So now how do we train? So we have a setup ready. We know that this is the Markovian formulation for my problem. This is all the actions that I can take, and this is all the states that can exist in this problem domain. And then I have to maximize my DCFR. This is my aim. Now, how do I do it? I need to collect a little bit of data. And this data is not labeled data or supervised data, just some data from that previous domain space or problem space. Now, what do I do is, I'll let the agent explore. Okay, start with the random state, start with the random action, go to the next action, go to the next state, next action. That the sequence that you see on the screen, right? S0 to A0, then S1 to A1, then S2 to A2, and go for it. And some point in time, I'll call it, let's terminate it now. This is one episode. Now I will let the agent do this exploration over multiple episodes. If it is a chess game, I'll let it play. Like I'll play it with a computer. Lose, lose again, lose again, lose again, lose again, win, lose again, lose again, lose again, win. Then it, over that episode, it will actually start guessing better actions in course of time, unsupervised. Okay, nobody is teaching it anything as like a teacher student model or anything, nothing. It is exploring on itself, because the problem definition is concrete, because I know what states I can take, I know what actions I can take, and within that space, play, and figure out which is the best possible action. So in effect, what we are trying to do is learn a policy, something called a policy. So what is an agent? It is nothing but a mapping from a state to an action. Given a state, take an action, and there is a policy that is guiding it. Now in our map example, let's imagine my policy just goes left. That's my policy. I'll only take left strides. So I'll go left, left, left. I'll never reach the institute, right? Another policy is only go right. Again, the same thing. Another policy is like take random steps. I may or may not reach, or maybe I'll just go around like a headless chicken and I'll never reach. So these are all policies. Now what we have to do is we have to learn that one policy that is optimum in some sense that will make me win the game or reach the training institute after some point in time. Now, how do I say what policy is optimal, right? It has two values associated with it, called a value function and a Q value function. So value function is nothing but, for a particular policy, how good a state is. Okay, I'm walking, and at this point in time, looks like my distance has reduced. The distance to the training institutes has reduced by 5 times than I started, which essentially means that's my state, which is a good state to be in. Whereas when I started from somewhere and my distance increased by 5x, very bad state to be in, right? So the policy gives you, or basically it's a value function for the policy. If I follow this policy, I'm in this state. And how good or bad this state is a measure of how good my policy is indirectly, right? Another thing is Q value function, which is basically how good an action now is given the state and for that policy. So I was following a policy, I ended up in a state, and now from there I take an action. Okay, that's also an indirect measure of how good or bad my policy is, isn't it? Are you convinced? So these are, look at the equation, your expectation came. Now that's the actual function that we will bank on, Markovian process. Given a state and a policy, what's my reward? That is the value function for a state. Now, Q value function for a state, given a policy, given a state, and given an action, how much is my reward? How much is my DCFR? And if you look at it, it only takes future states, T plus K. Okay, it only considers future state because we are maximizing the DCFR. And these are indicative scores of how good or bad a policy is. Now, what's our intention? We need to maximize either this value function or this Q value function and learn a policy, just like any other machine learning. Yes. No, actions, we will trace that path for every actions going further. That's how we compute the rewards, right? So we have to trace the path till some termination criteria. Yes. Mm. Mm. Yes. The action is in. Because the action is accounted within the reward. The reward is computed as a function of that action that is taken, right? So, yeah, I skipped one slide. Sorry. So basically, let me see if I have that slide. Can someone help me? Uh, that's a slide I skipped. So basically, when you are going from AT to AT plus 1, you secure a reward. And that reward, that red circle over there, is basically, it can be a stochastic process like a statistical model, or it could just be a function. And particularly when we have the fitness function kind of a functional representation of the space, just evaluate that function given your ST and AT. So you will take that path from AT to AT plus 1 and you will secure that deterministic reward that we have coded inside our Markovian process. Same goes for your state transition probability matrix. When you take when you take that action, you reach ST plus 1, right? What's the probability of reaching ST plus 1 from ST? That's probability, transition probability matrix. So P and R, you know ahead of time because you have done the problem formulation with respect to the Markovian decision process. Completely depending on your problem statement. Sometimes yes, sometimes no. Policy need not be constant. That's, we will come to that, adapting. So now we are at the learning phase, right? We are trying to learn the policy now. How do I go back? Okay, so that's how we going to learn the policy. Now, let's go a little bit deeper. A policy, we have to learn a policy, right? So it can be done via Q value learning or just looking at the value learning. Value learning is basically called policy learning, and Q learning is basically when you try to bank on the Q value of the policy. So what is my PPO is proximal policy optimization. So this is a algorithm using which I can learn my policy, and this is the only algorithm that I'm going to talk today. There are multiple other variants out there. So what do I need to learn? I need to learn a mapping between state and action. That agent square box that you have seen, and that's basically your policy. How does it learn? We already said that it will learn via episodes. Now in PO or policy optimization, we will only look at the value function. And what's the value function? How good a state is. We will not look at the Q value function where how good an action is, because that is actually captured within the probability itself, right? Pi of AT given ST, if it is high, that action is inherently preferable with respect to the DCFR. And if it is not, it's not. So basically in algorithms, either we bank on value function or Q value function, or there are some hybrid algorithms also which banks on both of this. So here today I'm going to only talk about the value function. Now what does PPO does is, this is a very classic problem inspired from GANs, generative adversarial networks. So we try to learn two networks which are competing with each other, and finally they'll learn from each other and the task gets accomplished. And actor critic is also something like that. So it's like one side of the network trying to learn a policy towards best action. The other side of the network critiques it at every step, saying that is a state good or bad? Now, if the state is bad, you go and tweak your policy. So PPO is also a parametric optimization technique, which essentially means that we will learn a deep learning model. Why deep learning? I think you already said that. What if your action space and state space is humongous? GA won't be able to handle it. PSO won't be, any of those algorithms won't be able to handle it. You need deep reinforcement learning, DRL. And it's basically RL on a deep learning network. So what does the first piece of the network does is, it will learn the action probabilities, which is pi of AT given ST, given a data. And you will basically indirectly compute how good or bad an action is without looking at the Q value. Okay? And we will bank on a loss. We have to track something, right, to make sure that we are proceeding in the right direction. So in a supervised learning, this is pretty easy. You have a labeled data, you compute a error on top of it. Here we don't have a ground truth. So what are we going to track? Okay. Now, this is what we are going to track. I'll come back to it in us. Oh, maybe I'll go with this. So this is the loss that we are going to track. What are we going to track? We will try to get that quality function pi at one instance of the network, then tune the network parameters theta to reach a different state and compare this state with back in the time. And this could be immediately 2 or 3 or 4. The comparison can happen over 5 time steps or 10 time steps, depending on, you can tune this as a parameter for the algorithm. And then you will actually track that as a loss. And after every n iteration, if you're looking like the loss is going downward, you will copy this theta from 10 steps back to current step. Or you will do a linear combination. Somehow you merge the weights at this time step with 10 time steps back. Then you do another 10 time steps and compare if the loss is going down or not. If it is yes, merge. Then go again, merge. And in a probabilistic sense, at some point in time, we will reach a convergence saying that our L theta is not changing anymore, or like it's stabilized, just like the convergence in GA that we have seen. Now the other, so this is just a visualization of that. So let's say this is the old theta, the blue box, and we get all the pi of AT given ST for all the actions that can be there at that time from the action space. Same thing we compute from this space, the current time step or the current network theta, and do expectation comparison over this and call it as the loss function. Now you traverse through this for 100,000 time steps or 1 million time steps or 1 billion time steps, depending on the problem complexity, and you will reach at a convergence. The other side of the network is the critique network, right? So we talked about the action going this thing, and critique network, with at each time step, it will give you a value estimate, right? You took this action, you ended up in this state. How good of this a state is this? Now you use this to actually compute an action score, this term over here, A cap T, for all actions you have taken till now, and use that as a tuning factor for your L theta. So now you are going in the forward direction. Every time step you take, somebody is going to critique you. You take the critic feedback and add it into your loss function while you move ahead. And using this, interactive training or interaction between this and interaction with the environment, you slowly start to learn which action is better. So after all this, this is how the neural network looks like. So we won't train completely different neural networks. That would be computationally wasteful. So we will actually have the same front end of the neural network, and the backends, or like the last 2 or 3 layers, will be different for the actor and critique, and you will have a joint training mechanism. So what do we get after all this training happened? We traveled from S0, took an action A0, got a reward R0, reached S1. Now what should I do from this S1 is, I can take A1 action from S1, A2, A3, etc., etc. That's all the potential actions that I can take in this action space. Each will have a probability predicted by the policy. Policy will tell you which each action has a probability. Now you take the action which has the maximum probability because it's learned from the policy. So this is how we do policy learning. So we put all these back into the reinforcement learning framework. How does it do? How does it look like is, we have the environment, reward function, and state transition probability. The green boxes, we know it ahead of time. That's why I highlighted it as green. This is part of your problem formulation, the Markovian decision process. It could be, the reward function could be functional or stochastic, or depending on your problem statement. And using this, that orange box is our agent that we train, and it will give you the set of actions that are required to achieve your goal. Okay, so this is how RL is trained. Now let's come back to the original problem statement, flight scheduling. Quick recap, what are we going to do? We have to assign an aircraft, 2 pilots and 3 crew members for a flight. Now, subject to what all are the constraints? We need to schedule all the aircraft under consideration, schedule all the flights under consideration, make sure carbon emission and budget constraints are met, and crew constraints, crew operating hours, all of these are met. This is our constraint optimization problem. Now, where RL helps is the additional things that I have put it under consideration. Let's say a flight ka revenue changes depend on a flight priority score, rush hours, festive seasons, etc. This is from market demand. Somebody is calculating the market demand score, and we call it as flight priority. And the priority score changes, essentially changing the revenue, which was not in the case of GA. We had a fixed estimated revenue. Now, the other thing is weather conditions, as you can imagine, right? All the practical things that can go wrong around a flight scheduling, like weather conditions, flight cancellations, crew calling it a sick day or whatever, crew fatigue, etc. All these will impact your operational cost, your fuel cost, your carbon emissions. I am just quoting these three because that's what I have considered as part of the current problem statement. Now, using this problem statement, how do I frame the RL? I know that my environment has different parameters. Parameters in this case is my budget cap, my carbon emission limit, crew working hours limit, etc. Action space, all the action that I can take, which is essentially for flight 1, pick aircraft 1, crew 2 pilots, 3 crew members. This is my action space. This is all the action that I should take. Now, what is my state after getting all these taking all this action or whatever? What's my state? Current state is how many more hours the crew has, so that I can take a decision on when to place that crew member or not. How many more carbon emission that I can take without hitting the limit? How many more flights can I schedule without hitting the carbon emission limit? How many more flights can I schedule based on the operating cost so that I will hit my budget? It becomes a sequential scheduling problem. You take one action set at a time. Are you with me? So you schedule flight 1 with all the resources available, and you compute what are the rest of the remaining resources available. Then you schedule flight 2. Then you reevaluate your scenario. How many more resources do I have? Then you schedule flight 3. Now, sequential scheduling. What's the advantage here? After scheduling flight 2, you received a news that the craft that you thought to schedule for flight 1 broke down somewhere. Bad example, sorry. So it is non-operational. Quickly, you can adapt to that and pick the new available flight and schedule flight 3. This becomes a sequential scheduling problem. Essentially, make it an adaptive scheduling problem, and you will be able to factor in all the changes that is happening in your environment, which was not the case with LP, which was not the case with GA. That's where RL shines. Now, coming back to your question on policy adaptation. Yeah. You can. Yes, it shouldn't be. Yes, yes. So for the example problem that I have, implemented, I have only considered 3 things. Now you can actually pre-compute a sequence of flights that I need to schedule. It could be from the time probability, right? So I need to schedule tomorrow's flight first, rather than scheduling 5 days out. One consideration. Another consideration is priorities. Okay, I'll schedule all flights for tomorrow, but then hold on the flights for day after tomorrow. But I'll schedule a flight that I have high hopes on because it has very high market demand. It is going on, I don't know, before some Coldplay concert. People has to reach some place. So that flight is gonna get overbooked. I know that for sure. So maybe I'll schedule that first and allocate crew. So these are all the considerations that you can plug into the RL to even pick that decision on which flight to schedule next. And it can be preset conditions like the Coldplay concert. I need to schedule that. Or it can be adaptive constraints saying that, oh, if I schedule this flight today, maybe I will lose on flight 4 because airport constraints. So I have scheduled a flight from Pune to Abu Dhabi. So that craft can now take off on a flight from Abu Dhabi only, right? So imagine that flight got some repair work or broken down at Abu Dhabi airport. What does it has to do? I cannot schedule the F4 that was supposed to take off from Abu Dhabi. Either I do alternative arrangement for that F4 at that time or cancel the flight. These are all constraints that you can bring in. This is all part of the problem definition. I haven't done it because it's a simplistic. That's the time steps for the training algorithm, the T. The adaptive constraints, I haven't, so I did not put it as R of T, right? Because it was a simplistic problem statement. I just wanted to convey the idea of how policies learned. So the T over there is time steps of episodic training, not the adaptive time series data. So when time series data comes, it will become a time series adaptation. And then, well, let's call the, instead of T, let's call the time steps as K or something at that time. So it becomes a time series. And the beauty is RL can accommodate it when it comes to that. You with me? Convinced? Cool. So that's what how we do the flight scheduling. I have implemented a very simplistic example with like scheduled 50 flights. I have 80 aircrafts, 120 pilots, and 190 crew. Fitness function was pretty much same as your GA problem statement. The only added factors here are weather-based constraints, like carbon emission became nonlinear with respect to some weather conditions, fuel cost became nonlinear with respect to some weather conditions, etc. And this is how the policy learning happens. So this is the DCFR or PPO policy reward increasing. So as you can see, when episode gets increased, your policy is going upward, which essentially means that it is learning. And after a certain point of time, ad hoc, I called it as 1 billion time steps, 20,000 episodes got run, and I stop it. This is my termination criteria. I can actually do a stabilization criteria on this policy and say that only after this become a flat line terminate. I did not have that much time, so I didn't do it. So we can do it based on your considerations. If it is a crucial problem, if it is a lenient problem, etc. So basically, the point is the policy is learning. Policy map now we have. Now using this policy map, I have done the flight scheduling, and you can see. Oh, you can't see. Can you see? So the first panel here, if you can see, don't try to read into it, but you can see that not many blobs are overlapping now, right? Can you see that? As opposed to the GA problem statement when that aircraft 10 got assigned to 10 different flights. There are some duplicate assignments still here because we penalized it rather than hard-coded. So there are some duplicate constraints, but that is okay when we factor in the time constraint. So the A10 can get scheduled to flight 3 and flight 30 because 30 is going to fly 3 days after, something like that. So it is taking care of that. Same with crew and pilot assignment, duplicate assignment gets reduced, or like you can see, right, that landscape, that points are like distributed over that square now, which essentially means that diversification happened because the policy learns. And this is the crew overworking hours. As I said, we cannot completely avoid it, right, because of practical constraints. I haven't factored in the time data on this example. So some of the crew are still overworked, some of the crew are still underworked, but it is better than what GA has. Oh, and carbon emissions, slightly more than the legal limit. Budget, little bit more than the the set budget, but we allowed both of these with which are like penalties. And since it is sequential scheduling, what are the advantages that I got? I got taken care of for the time series data, for adaptation, etc., etc. And this is a super cool algorithm which can change. Now, I think I'm concluding. So RL for flight scheduling, we have seen that it can handle dynamic environment. So how does it handle this? It actually acts as a pull-based system rather than a push-based system. Like GA, you have to pre-compute all the data and go and press a button to trigger it. And it will give you a flight schedule for next 3 days. Then something happened. You have to come back, pre-prepare the data. Oh, 3 flights got broken down. I have to remove that from the available aircrafts now. Prepare the new data, come back, press the button on GA again so that it will schedule. Whereas RL is like a continuous system, an agent kind of a system. that sits inside the environment, pulling all the data from the environment and reacting to any changes in the state variables. Okay, so it's a pull-based system rather than a push-based system. And we have several practical constraints which I did not talk about. So in the training, we have several parameters to check that non-linearity that we talked about in GA, exploration versus exploitation. Here there is like entropy constants, etc., that we can tune as parameter of the network to hit that balance between them. Environment is not in the capacity of the agent, right? Environment is whatever is there. So if a flight got broken down, it's no fault of the RL that the flight got broken down. Just that it will know that the flight is broken down and it will tweak the schedule for the remaining day or remaining month, accommodating that breaking down of the craft. So it is runtime because the training is once, right? So even if I train this policy for 1 billion time steps, let's say it trains for 5 hours, it doesn't. And it's a one-time process. After that, whatever happens is very much faster than GA convergence. So it's faster compared to GA convergence, and it can do sequence scheduling as opposed to other algorithms that we have. So I would want to conclude now over time, but it's okay, I guess. So we looked at constraint optimization as a problem. We have seen different algorithms, LP, which offers simple, fast solutions, but it will only work for linear formulation of problems, simple problems in general. GA offers support to nonlinear real-world problems, as you have seen already, but it requires that math formulation to be carefully crafted. Now, if GA versus RL, if we can compute that weather conditions ahead of time, right? It's a weather forecast. So you compute that weather forecast ahead of time, put it in a vector space and plug it into GA, it can still work. So anything that can be computed ahead of time as an estimate, GA can still work if the action space and state space is limited. But think about a scenario where this flight breaking down happened. And I'm like, oh my God, 3 flights broken down. I have to come back here, edit my data, and then press the button on GA. And I'm like, oh my God, it's not converging. Sahajair will get bankrupt and close down in a jiffy, right? As opposed to RL, which actually supports in itself that adaptive environment based on the learned policy. Okay, but then I still have to call one thing out. Sometimes RL is an overkill. Don't think that, oh, this is the super cool algorithm, I'll always go and train RL. What if it's like a very offline logistics kind of a scheduling problem? And MILP based solvers are existent for like decades now. People are using it very successfully. So when you choose a strategy for a problem at your hand, always be mindful about the practical consideration, cost, latency. Don't do that overkill that everything is agentic AI today. So I'll always deploy an agent whenever required or whenever it's not required also. So be mindful about that overkill problem. Use suitable tech choices for the problem statement in your hand. Also, I want to call out the second thing. First thing was the overkill problem. Second thing is domain knowledge. Nowadays, the tendency is like, oh, there is this super cool model, Mistral or Llama or OpenAI GPT is available. So domain experts can go and take a day off. It's not like that. As long as your GA formulation, that mathematical formulation is not correct, as long as your Markovian decision process ka formulation for RL is not correct, nothing is going to work. Take my word on it. So domain expertise and getting data and information from domain experts are still important, even though in the fast changing, evolving world of AI. So that's the second thing I want to call out. Yes, please. You can. You just have to plug in a feedback loop. Yeah. Again, be mindful. RLHF, people have successfully used it on text data problems. When it comes to tabular data problem and your human who is doing feedback doesn't know what is he or she doing, you are going to mess up the system. So tabular data or structured data processing versus unstructured data processing for a human, very different. You can easily read an article and grasp what it is, and you can even critique the article. Can you sit and look at 10,000 Excel sheets and drag insight out of it? That's where a model does better job than a human. So don't introduce feedback loops when you know the feedback is, when you are absolutely not sure about the feedback, don't introduce feedback. RLHF works great in text data. That's all what I'll say. Cool. Thank you guys. Thank you so much for the patience.